everybody. Welcome back. Last from the break. I think we have one more break after this, and we'll be into the finish. So thank you everybody for your continued attention. Hopefully you got some coffee and are feeling good this afternoon. We have a really exciting panel coming up for you for the next hour, and at the end we'll hope to take some questions. But the topic of this panel is all about zero knowledge and hardware acceleration. So many of you who were at this morning's session saw that I presented about ZPrize and the second iteration of ZPrize. So I was the organizer of the last ZPrize competition. And I think everybody on stage that you see here was also part of that in some way, shape, or form. And in general, these are a group of experts that focus on hardware acceleration for snarks and advanced cryptography generally. And I'm going to let them share more about each of their stories here in a second. But that's the topic, and really excited for all of you to join us. And with that, maybe let's go down the line here, and maybe just can you gentlemen introduce yourselves and talk about what you do and what your company does.
Hey, I'm Rahul. I'm at Jump Crypto. Jump trading, Jump Crypto, sort of known in like the trading HFT quantitative trading space. For the past 7 years, we've done a bunch of different crypto stuff, and recently we got into ZK because we're all excited about kind of the infrastructure, and the applications that can potentially arise from it. So we're super excited about ZK in general, and I think we want to participate in kind of solving some of the harder problems in the space.
I'm Hamid, Salehi. I'm part of the product marketing team at AMD, part of the adaptive and embedded computing group. So that's the team that made all the FPGAs, was Xilinx, and was acquired by AMD. Pretty active with the ZPrize, supporting Alex and the rest of the team. So we have provided the FPGAs that were used in ZPrize, and looking forward to continuing our work with the community.
Hello, my name is Omer. I'm the CEO of Ingonyama. Like every successful technology, we have software, algorithms, and hardware. And my company goal is to basically provide the infrastructure, the hardware layer, and a bit of the software, to run the hardware for for ZK and more generally, or broadly speaking, advanced cryptography. I'm the CEO of the company, so I'm doing not the most fun things you can say, but I'm enjoying working with a very small but talented group of engineers.
Awesome, thank you guys. Maybe let's just start out. So those of you who are not familiar with the semiconductor kind of hardware world, maybe we can just I'll define a couple terms for everyone quickly that are relevant here. So, most people probably heard of ASICs. If you're familiar with Bitcoin mining, ASIC stands for application-specific integrated circuit, right? So this is like a very specific, program that's basically hard-coded onto the silicon, and it's very efficient. As a result, you have FPGAs, which are fully programmable gate arrays, which are kind of a little bit more programmable, and I'll let these guys who are experts tell you more about that. And then you have graphics processing units, right? There's other things too, but I think at a high level, like when we talk about specialized hardware, that's what we're talking about. And the first question I wanted to pose to the group is, what problems in zero knowledge, when we talk about hardware acceleration, what does it mean? What does it mean to accelerate a zero knowledge proof? Like acceleration of what? Like, can you guys just kind of share what permits acceleration in this field?
So the problem of ZK pieces, we instantiate it today in the space as a prover and a verifier. And usually we take this trade-off, or we use Starks, which has this trade-off that we get a very short proof, and verification is also extremely elegant, but we pay in compute, in memory, blow-up of the prover computation. So usually when we talk about acceleration, it's a bit tough to define exactly today the boundaries, but at least what we aim for is to make the user experience acceptable for the right application when we focus on the prover, right? Basically, so it's taking the entire prover algorithm and making it run in performance cost that makes sense eventually to the application.
Maybe a couple of points from kind of a, business perspective. You look at proof generations, we look at proof per dollar, proof per time, and then proof per power. And the goal is to make this as efficient as possible, especially when you have wide deployments. When you start a project, maybe you might not care as much how long does it take or how much power especially it consumes. But when you're thinking about massive deployment, if this technology is going to get adopted at that scale, then these parameters become important. And when we say hardware acceleration, how to make those orders of magnitude more efficient compared to what you do on a CPU or even on GPUs, for example.
Okay, cool. Thank you. So hopefully that helps folks understand. I think the last thing that Hamid mentioned, I want to just highlight. I kind of, it's a bit of a trick question. Is like, what do we accelerate? Well, in some cases, like acceleration may not be the goal, but making something more efficient is the goal, right? And so, there's sort of, I like to think of broadly 3 different, axes in which we can improve, and hardware can be useful. And I think one is latency, right? So the generation of a single proof, making that as fast as possible. Another is throughput, given a single unit of time, as many proofs or as many verifications as possible in that single unit. And then efficiency was the last piece, which is very important from a business standpoint oftentimes. Certainly in mining, that's one of the most important things. And that's the cheapest cost per proof or verification. Cool. So actually, since we're talking about use cases, maybe I'll turn it over to you, Rahul. Like, what you guys at Jump have a lot of really interesting public goods work and open source software work that you guys do. What use cases do you see for ZK snarks where you think hardware acceleration will become important sooner?
Yeah, I think there are a few use cases of ZK in general that make sense. So like, in terms of like the business use cases, right? Like we're all concerned about like, what the latency is going to be, like what the cost per proof is going to be. Where does that matter? There's a lot of applications in crypto, right? Like let's just I'll take a simple example. So let's say you have like a price oracle, right? And let's say you're generating proofs as a result of this price oracle, or just a ZK oracle. I'm sure you guys have seen this application, in a bunch of different places. But like, if you can't generate proofs quickly, then whatever application or client that's going to be consuming those proofs isn't going to be like sort of incentivized to use that application. And so this becomes the bottleneck for a lot of different applications where the cost per proof and also the latency per proof becomes like very important. And that's the case with like a large number of applications. Like another one is like sort of, cross-chain messaging protocols where like for the user, like latency is in a very, very important dimension. When you want to when you want to do anything like across different chains, like you want that experience to be seamless. And so it becomes a huge issue when, all these sort of systems like want to move to ZK, but you don't have the appropriate like horsepower to actually like, enable these applications.
Actually, I think I'm going to change the model here a little bit, and I think maybe every one of these individuals, as they get the mic, I'm going to ask them a new question. So they don't have a lot of time to think. Everyone's going to have the same time to think of an answer. So, okay, so now that you have the mic, Hamid, I have a question. So, Hamid is here from AMD. Some of you may have heard of it, and a question that I would have for you is, ASICs are, we've been told that, ASICs are the holy grail for compute, with regard to efficiency and, throughput and all these things. I mean, if you look at Bitcoin, ASICs obviously can produce more SHA-256 hashes per second by orders of magnitude than any other piece of hardware. So why don't we have a ZK ASIC today? Like, why is there not already an ASIC for ZK if we're all here and we believe that this technology is the future? Can you kind of give me a little bit of your answer to that?
Yeah, sure, absolutely. And this is kind of a pretty familiar paradigm, right? If you look at, what happened during Bitcoin mining, as a matter of fact, people started mining on FPGAs, and then after a while, started creating ASICs. And even, kind of outside mining, pretty much any area you look at, communications, different workloads in data centers, you see that a lot of time when the new technology shows up, people start designing on FPGAs, and then there is a crossover point. At some point, people start designing ASICs. Now, there are pros and cons of each approach, right? So with ASICs, obviously, you are going to do absolute customization. You can really make it perfect for that specific state machine, for that specific function. Now, the drawback of doing an ASIC is, so number one, ASICs are very expensive. You're going to spend tens of millions of dollars doing an ASIC. And then, God forbid, if you make a mistake, that's another tens of millions of dollars of, mistake that you have to do another tape out. And then if the protocol changes, if anything changes, so that ASIC might not be as efficient, and another ASIC shows up, and now all of a sudden, that design, again, you have to redo it. So there is a lot of risk associated with doing an ASICs, and you want kind of the technology to reach a level of maturity before you even consider an ASIC. Especially kind of moving to a smaller process nodes, 5 nanometer, 3 nanometers, those tape outs are extremely expensive. You're talking about $50 million, $100 million to bring a chip to market from ideation all the way. So the alternative approach to that is to use an FPGA, which basically with an FPGA is a blank circuit, meaning that you can give it any definition you want. So exact same circuit that you can design on an ASIC, you can design on an FPGA, exactly same performance. The compromise is, because it's a flexible programmable circuit, it's going to be much bigger in terms of silicon area. Approximately, you are going to consume 10 times the silicon area to implement the same function you can implement on an ASIC, on an FPGA. So that's, the extra cost you have to pay in terms of the device itself. But the beauty of it is you basically can put a design on an FPGA, and then if you realize that the protocol has changed or you made a mistake, you can just go and dynamically change it. So basically, you're not going to go incur that cost of tape out that, as I said, for a small process node might be somewhere in the, $50 to $100 million, depending on what you're designing. So you're looking at the ZK, and I see all these meetings and sessions and everybody coming with something newer and, a different way to implement. And, our friends here, are working on different approaches and publishing papers. And I think that's an area that still is evolving, and I think is going to evolve for the next couple of years. So considering that, doing an ASIC is somewhat of a risky proposition, because if things changes, forget making mistakes. Assume you're not going to make any mistakes. But if anything changes in the protocol, now all of a sudden, you have to go redo it. And then, we work with a lot of startups. Some of them say, okay, how about if we create certain functions and make it a programmable ASIC? So it's somewhere between an ASIC and FPGA. And my response is the challenge is then it's not an FPGA, meaning that if you make a mistake, still you might need to do another tape out. And then it's not going to be super efficient, meaning that somebody else might show up with a perfect ASIC, and then you're not going to be as efficient as well. So you have to be really careful if you want to kind of embark on the ASIC journey. And also doing an ASIC, especially for smaller startups, there is a whole lot associated with doing a good ASIC. Like if you look at Bitmain for the mining space, so they have a strong relationship with TSMC, great connections, and they have been in the space for a long time. Doing an ASIC is not just about doing a tape out, it's about the supply chain, the quality, the validation, and all of these are pretty sophisticated technologies and expertise. And even if you do all of that, say during the pandemic, assume you have done everything right, because you are a startup, then you don't have a relationship with TSMC, you have to go through a broker, then even though you have an ASIC, you might not be able to actually get it made at quantity. So there is I don't want to take the whole time of the panel, but it's a pretty, the way I put it when I talk to startups is be extremely careful when you think about ASICs. It's not as trivial as it sounds. It sounds exciting, but you have to be super careful.
Awesome, thank you. And Omer, follow-up question for you. So I feel free and comment on that question, but also I think, you're looking at, I think the way I would frame the question, maybe a little bit specific to you, is, Ingonyama is here to produce, to produce proofs, and depending on the context, you're going to choose the right tool for the task. So again, comment on the last question if you want, but also maybe you can say, like, depending on the context, how do you decide what tool to use in terms of hardware?
Yeah, that's true. We have, the way that we like to work is starting from the client, what they need, right? Let's define the problem, and let's see what makes the most sense. So, as we mentioned before, it might be that we want to optimize on performance, on cost, latency, throughput, and so on. Might be that we are forced to work in some kind of a cloud environment, right? So today, all of the big clouds, they allow access to instances with specialized hardware, like the ones we mentioned here, GPUs, and FPGAs. And yeah, the business case should be defined, and the more we can define the problem, the easier it is to come up with an appropriate solution for that. Now, what I can say in general is that today, you know, it's a very small, it's a niche, right? Like hardware for ZK, and what it means is that most of the projects, and I guess like for some of you sitting here and working on projects, they are still a small project, right? It's not like we are at scale and we need to concern ourselves with how to mass produce hardware at scale. So usually GPUs are kind of like first line, right, of solutions. They should provide the good amount of acceleration, I mean, generally speaking, to solve a broad class of problems. So I think that for those of you, or at least it's also true for us and kind of how we approach it, like the market, we start with GPU. It allows you to iterate fast because it's like programming in software. I mean, you don't need to worry yourself with all of this, like, you know, the bits level. It's already kind of like high level, and you can code everything and get results and iterate relatively fast. So usually GPUs, I mean, again, for those of you working and building now on CPUs, eventually when the project is getting to some stage, you get to a bottleneck, like you need to scale it and you need to accelerate. I don't know, you want to lower costs or you want to make user experience latency, right? You want something to run at 2 seconds instead of 5. So then I suggest let's move to the GPU. And today, thanks to initiatives like ZPrize and some open source code, we provide an open source library and we work with teams on making these adjustments to kind of run everything in GPU. This is kind of like first line of solutions. Now, once you start to hit growth and actually get to a more specific problems, then FPGAs can become the right tool, right? You know, to give an example, so in Filecoin, for example, so Filecoin, like the blockchain that exists for several years now, and they are running today on GPUs. But because GPUs are power hungry, we actually consume, it's not about electricity, but because they are power hungry, they are also big because they need cooling. And when you move to an FPGA, which is requires much less power to achieve basically the same performance, you can have a much smaller form factor. So when you think about it, when you run some Filecoin, it's not called mining, it's like sealing, but when you run it in your data center, you want to to utilize your data center to the maximum. So you want to work, it's like, you know, pizza box servers, and this is where FPGAs can fit nicely because they are tiny, right? They are small compared to GPUs. So this is like one example where you say, okay, we've worked with GPUs, now it's the time to upgrade to FPGAs, right? So at least this is our approach.
Awesome, thank you. And Rahul, I've got a question for you here. So specifically to FPGAs, so Jump Capital uses FPGAs for a variety of applications outside of just crypto. And I guess maybe for those folks in the audience here who are developers and are like, oh, this sounds cool, I want to accelerate, you know, this or that, or my snark verification, you know, and FPGA sounds like the right tool. What would you say as a, you know, what advice would you give folks who are looking at using like FPGAs specifically, who might be going to a GitHub repo for ZPrize, say, and they're like, whoa, what is this language, Verilog, and how do I even start here? So I guess, how do you think about that, or what advice would you give folks to think about programming in the FPGA paradigm as opposed to, you know, the traditional paradigm?
Yeah, Jump does have a lot of sort of like in-house FPGA expertise, largely because, you know, on the sort of like quantitative trading side, there's, you know, a bunch of work that has to be done on that. I can't really comment on that because I don't really work on that stuff. But what I do know is that, you know, especially with the stuff that we were working on for the ZPrize, in particular, like accelerating some core primitives like multiscalar multiplication or number theoretic transforms, like FPGAs are a great sort of tool for you to use in terms of like prototyping and understanding like what the problem space is, and then at the same time giving you like the performance, you know, that Omer mentioned in terms of like, you know, comparable performance to GPU. The thing that is sort of, I think, understated on the FPGA side is like the data bandwidth. So you can do a bunch of these, you know, awesome computations on an FPGA and like you can make it super fast, but you know, a lot of FPGAs and, you know, on sort of like the cheaper end don't really have the same like throughput or data bandwidth that you really need to kind of scale these computations. So like if if the data bandwidth takes long, if the time to transfer like data from your host to your FPGA takes longer than actually doing the computation itself, then you haven't really saved anything. You could have just done it on your CPU. You could have just done it on your host. And so like in particular, like there's, you have to really think about like what type of FPGA you're using, what architecture you're using, to make sure that like, like this was actually the case, for some of the NTT computations that we did, where like the PCIe just wasn't sufficient to ensure that like when you're doing these computations that you're actually like gonna get a speed up in real applications. And so that's something to consider. I think there are FPGAs out there that do support like high throughput sort of data bandwidth, and like you can use those, but you just have to be very careful about your selection process there.
Awesome, thank you. And yeah, it's just like AWS, for example, folks may or may not know, has instances you can use. And of course, Hamid here, AMD Xilinx, manufactures these, and I want to ask his opinion about. Actually, I want to ask your opinion specifically about what Rahul just mentioned. You're thinking about you want to create FPGAs to potentially serve a certain category of problems. How do you think about designing them with in mind, with those trade-offs in mind of like data bandwidth versus compute, et cetera? Like, how do you think about it from the perspective of designing new FPGA boards for a specific category of use cases?
Yeah, so I kind of want to touch base on the previous question a little bit in terms of you asked if somebody wants to start with FPGAs, what should they do? So that kind of, so first I have to say designing on an FPGA is not an easy task, just right off the bat. And these two guys sitting next to me, they are geniuses. So this is a very complicated process, fairly. So if you're coming from a software background, it's a whole different way of thinking about how you design something. And kind of tying that to the question that Alex just asked me, you really have to think about your architecture. It's very different from the way you think about as a software engineer. You come with an algorithm, and maybe if you're doing it on a GPU, you think about, okay, how do I use the CUDA and some parallel calculation? Doing it design on an FPGA, you really have to think about your circuit the same way you think about designing an ASIC almost. So the data hierarchy, the data weights, the way you communicate to the memory, the way you use the internal memory of an FPGA, is all going to make huge difference. Also, some FPGAs have access to high memory bandwidths, and then how you interact with that, and even design the memory controller that can read and write data from that memory. All of these are very, very important. Another thing that we tell people who design on FPGA, we tell them that you really have to think about your whole application, because if you accelerate a part of the application by 100x or 1000x, but then you have one little bottleneck, which Rahul mentioned, one of them, then all of a sudden it's all for nothing, right? And all of those kind of acceleration at the end, you look at the whole application end to end, it might not be as useful. So you really have to think about how much bandwidth do you need to the host to make sure that doesn't become a bottleneck, for example. And if you're using too much, is there a way to change the way you pipeline your data? FPGAs are extremely powerful when you stream data as opposed to read and write from memory. So how much you can kind of rely on streaming to really makes things done faster. And I have to say, I have seen teams, and even ZPrize, we saw that some teams did, implemented something on an FPGA, and a competing team was, almost, I think one case was 100x more efficient. So that kind of tells you that FPGA is a very powerful tool, depending on how you program it, it might make a material difference. Now that I scared everybody a little bit about designing on FPGAs, so there are ways. We have at Xilinx and now AMD, we have created a platform called Vitis, which is designed, targeted at software developers, basically. You can use Vitis and kind of start from high-level libraries in C++ and implement something on an FPGA to get a feel for what does it mean to design something on an FPGA. And we are trying to provide more documentations. We have a blockchain accelerator card, and we have provided quite a bit of documentation on how you actually use Vitis to start from high-level programming languages and implement something on an FPGA. Now, that process is a good educational tool. It's not going to be very efficient. So my friends here are not going to use Vitis. To really then design an efficient solution, first of all, you have to learn hardware programming languages, very like VHDL, that sort of thing. We have another workflow called Vivado, and then that's where you really design a circuit the same way you design an ASIC. And really, anybody who wants to kind of venture into that, you almost have to, learn how to design an ASIC, So it's a pretty specialized skill. But for companies that are thinking definitely, especially Omer mentioned something very interesting, that when you start testing something, you start on CPU, GPU, quick, make sure everything works. When you think about deployment at a scale, that's when you're going to start thinking about FPGAs, because you can design something that's more power efficient, faster, and it kind of pays dividend in the long run. The example of the Filecoin, when you're talking about massive amount of data that you want to seal and then store, power becomes really important, not just because the cost or the environment, which those are really important, but there is the issue of capacity. A lot of providers have limited access. The capacity is limited. So something that's more power efficient, you can increase your capacity. And also there is the issue of, transferring heat, which, might seem trivial, but it could be a huge challenge, in mass deployments. When you reach that stage that you think about really you want to, do deployments, then you think about FPGAs, and you kind of big chasm between FPGAs and ASICs. Because, you think about CPU, GPU, FPGAs, you are buying part off the shelf. And then you want to think about ASICs, as I said, you want to spend $50 million to do an ASIC. In your head, you have to say, can that generate at least 10 times what I'm spending? Can that generate $500 million so that I can spend 50, right? So that's kind of the math. And then, obviously Bitcoin get to that point, and, that's why ASIC made a lot of sense for Bitcoin. So.
I have to make one comment on what Hamid said, maybe an industry secret. So he mentioned Vitis as kind of like a high-level language to program for FPGAs, and then he said something interesting that, but real men are not going to use it. Like real engineers, they're not going to use this stuff. So we've kind of experimented with this high-level synthesis approach, and the C++ kind of level. And I have to say, it's like kind of like reminds me of generative AI. All of a sudden, like becoming like kind of like a level of intelligence that impressed us. So here as well, we can get like even better results than the handwritten like hardware description language by using the high-level synthesis. It got that good. And by the way, that's thanks to the guys at Xilinx and AMD. But yeah, so basically my message here to you is, if you want to experiment with FPGAs, then you can go to AWS. For example, as we mentioned, there's an instance with an FPGA. They have a shell. It's very nice, very easy to get it going. And you can actually program it in a high-level language and get it to run very interesting examples. Yeah, I mean, there's also, if you can find me after, I can point you to like real, open source examples of relevant finite field arithmetic that you can do using that form of programming to the FPGA. So.
Awesome. And I still have a question for you, so don't think you're off the hook, Omer. So wanted to turn a little bit to ZPrize and, the idea of, okay, so we have this open source kind of, or this competition where, everyone's going to submit various optimizations to an MSM, implementation, say, and a GPU. As an industry player, like, how did you look at that? What did you think of it? How do you use anything that came from it? And if you were looking forward and you were in charge, say you're in my shoes and you want to do the next ZPrize, how would you think about what problems to focus on? Sorry, that was 4 questions in one, but I know you can handle it.
Yeah, so ZPrize for us was a real game changer. So initially when we thought about it, we were younger as a company, and we looked on, in hardware, it's about IP, and how we can kind of like create a moat around this IP. So we were very careful with committing anything that's going to be eventually common good. Now, that being said, during ZPrize and also afterwards, we started to, we got to like few realizations. One, we as a company can actually leverage the outcomes of the results of ZPrize. So therefore, for example, we started this open source library for GPU and you know, if there's going to be a next iteration, I hope there's going to be a next iteration of ZPrize, and we're definitely going to participate at least in some of the tracks and contribute kind of, you know, to make, to push forward the market as much as we can and contribute our best. Another thing we noticed is that, you know, in ZPrize, at least the iteration that was like in 2022, it was about primitives. And at least for us, primitives are, they are part of the story, but they are not like secrets in a way. Right? So we're going to start in the future to also write much more like educational material on how you do this, like primitives, MSMs, NTT, you know, the playbook, or if I want to teach it in academia, how would I like approach it? Because this is, you know, it's like AI and matrix multiplication. These are like, it's tools, it's primitives that you should use, but the real magic is how do you combine all of this together, and how do you know, erase for a second the software implementation, sorry, not for a second, just like replace it with an equivalent hardware implementation that can leverage these primitives, but also does something, like it can do something else, like memory management, data flow management, and then this is where you can actually get to the 100x, 1000x performance. It's by taking the approach of end-to-end ZK acceleration, as we mentioned before, the entire prover, and not just the primitive, right? If it's just the primitive, so imagine you have the software, then all of a sudden you need to go from CPU, from host to device, then you run the primitive, then you go back. There are a lot of limitations, you know, in the interface, in like how you are kind of like coupled with the software implementation of the rest, how it forces you to kind of think in a specific way. So we even launched an initiative after ZPrize called Z Games, where we wanted to kind of like have a competition between companies around real-world implementations, for example, for Aleo, of entire provers, not necessarily with open source, for those that are not feeling comfortable like going full open source on that, but we thought that it might add some layer on top of ZPrize primitives to kind of like, you know, compare apple to apples. How do you approach and then like how do you engineer like some hardware solution for an entire system? So yeah, that's basically my points here.
Amazing, thanks. And then I think we might turn it over to questions here in a minute. I'm going to ask one more question. It's kind of going to be for each of you, and then we'll turn it over to the audience for questions. But we've talked to here, up to this point, we've talked a lot about how the prover is oftentimes what is the focus of acceleration or work, you know, with specialized hardware. To what extent do you see opportunities for optimizations or accelerated hardware used in the verifier side of SNARKs or STARKs, or pick your flavor of ZKP?
Yeah, I actually haven't thought too much about the verifier side, largely because the prover has been such a huge bottleneck. In a lot of applications, it's sort of like the whole point of like zero knowledge proofs in some sense, or like, you know, validity proofs, is that there's like the separation between like the verifier time and the prover time. And so I think on the verifier side, there are some interesting problems. Like, you know, I was just talking to a few folks here on like, you know, where you could sort of embed verifiers, you know, as like these custom gates within like virtual machines. We talked about this before, but there are some like potential improvements that you can do like on sort of that are kind of application specific, in the sense that, you know, if you have a verifier that lives on chain in some like virtual machine, in some like in programming language, there are some ways you can optimize that, but there's not something that I can think of, at least right now, that sort of like abstracts over all of that.
Cool, and I'm going to expand the scope of the question for both of you, as to, you can feel free and comment on that, but in general, like, even beyond verifier, like any other cryptographic primitives or techniques, maybe FHE, for example, that you all see, you know, we've heard it from a couple teams doing FHE. Are there other areas that you think acceleration, you know, or other areas that you think are ripe for acceleration? And feel free if you want to talk about that, Rahul.
Yeah, so on the verifier side, so the way we think about this is we rather make the verifier, so we rather see protocols that make the verification even easier, because then when you are verifying, you want to make sure you are kind of hardware agnostic. You can do it on, you know, mobile phone. You know, you really don't want to put computation load on the verification. So I may as well see the proving side gets more complex and then try to accelerate that, because that's where you can bring a lot of hardware to bear and then really make the verification as simple as light as possible, so that you do not need any sort of acceleration. Most, you know, general purpose compute, even a small, mobile ARM processors, what have you, should be able to verify fairly easily, fairly quickly. So that's kind of the way I think about the balance. That's how I think about this. But beyond kind of other applications, as a matter of fact, we have some projects on FHE. So we are looking at how FPGAs can accelerate that, and anything that's really, compute intense and that becomes a bottleneck, certainly FPGAs can play a role outside just the, the Stark and Snark that, we are looking at currently. So yeah, that's definitely an area under active research, and also the whole ZK on ML as well. So that's an area that we are looking at as well.
So I want to maybe address like another dimension, which is the client side versus server side. Because today we mostly talk about server side proof acceleration. And when you think about like, ZK and the promise of privacy, so you actually want to go to the client side. And it can also be surprising. Like, as a matter of fact, the way I'm thinking about it is how we can simplify ZK or find use cases for ZK that are like extremely simplified so that you can see immediate value in, core of acceleration. Like, to give an example, when you compare a ZK rollup to a ZK VM, so a ZK VM is being built like when it's a prover-centric, like you build a prover, and then around it you build, you can build whatever you want, like it can be a gaming application, right? But when you build a ZK rollup, so it's more of like Ethereum-centric, and you have like a lot of constraints to your system, and prover is one of them, right? So when in my letter of like simplification, ZK VM is like a simplified problem for acceleration. And, going client-side, I think also makes sense to talk about, indeed, other technologies. But, yeah, I mean, just to give you like some alpha, one example that one of my team, like teammates came up with. So imagine this like, TV, this, CCTV kind of like cameras, and that are programmed, or this IoT device that is like programmed to give you, like to trigger when there's like an event. And what do you do with all of the time that is like dead, right? Like, what do you do with these times? So it's either go to some cloud for storage, which costs a lot of money, or you need to do some kind of computation to kind of like, whatever. So if you can take these dead times and run a ZK proof to compress it into one single small proof, you can basically save, like, there is an economical value to that, right? Like, imagine this, like, it's one company, like a cameras company, IoT company, and you bring them value using ZK, which is like you save them money. So for them, it makes a ton of sense. And therefore, you need to run it client side, right? So I think that in the problem space, we do need to look for simplifications. Definitely, we need to address the main problems that we have in the space. So we shouldn't ignore ZK rollups. That's not what I'm saying. On the opposite, but we also, if we want to expand and we want to think where else, like provers and prover acceleration makes sense, we need to kind of like simplify as much as we can and look for use cases.
Amazing. Okay, great. I think we're ready to turn it over to the audience if folks have questions for the panel, which can also include me. So any questions for all and or any of us, please raise your hand. All right, great.
Hello, my name is Miloš. I'm from Ponos Technology. We are a hardware acceleration company, so we are doing like hardware acceleration in FPGAs for blockchain, and I have quite some questions, mainly for the FPGAs, because we are using also like the cloud-based FPGAs, Xilinx ones. So, and we noticed some first thing regarding the ZPrize, that like most of the tasks were not like really bandwidth like limiting. So you would do all the acceleration on FPGA and you could accelerate this a lot, but the actual bandwidth with the host was not the limit. And we see in the real application that we can do like, and this is also typical with GPUs, we can do much more computations on the hardware, and then we become like really bandwidth bottleneck. And mainly because like the communication interface for the today's cards available is only like PCI Express Gen 3. And the question is, is there a plan for this? Because this was not in the past, this was not the case. And for most general FPGA applications, bandwidth is not such a problem. It's more like computation. But for these in particular, because we cannot store, there is not so much memory available on FPGAs, the same as on GPUs, really the bottleneck becomes the thing. And the FPGA chips, they have a lot of transceivers on them, but it's only one fast PCI Express interface. So is there kind of a plan to go for like a PCI Express Gen 5 to get more throughput so that we can alleviate this bandwidth?
So I did not plug this question, just full disclosure. So we have a new line of product called Versal, and it supports PCI Gen 5, so you can get significantly more bandwidth, which solve a lot of these problems. We are going to have our early boards coming out later this year, and we are looking to kind of expand that portfolio. As a matter of fact, we are looking at 1 or 2 reference platforms dedicated to ZK, and there is a possibility that we might adopt the Versal, or we stay with the 16 nanometer, depending on, so we are going to start getting more feedback from the startups and the community. But yeah, so that's, our next generation, which is the 7 nanometer lineup called Versal. You get PCI Gen 5 by 16.
That's great. We are looking forward to this a lot. Thank you.
Another question around here, I think? No? Change your mind?
Any more questions? If not, we can, we can go ahead and, we got one more in the back.
Sorry, just a really silly question. If you had unlimited resources, what would you choose to, what would you love to see if there was unlimited resources of money and human resources?
You talking about for hardware acceleration?
Yes,
for
on the
ZK?
hardware.
Yeah. So I'll answer, I guess I can start by answering that since, I had to raise money for ZPrize and had limited resources with which to allocate. I think for me, the direction that I would like to drive innovation in the space is a bit like what Omer was saying at the end, is that, the initial focus of ZPrize was really about these primitives, right? So faster MSMs, and for those of you who don't know, MSM stands for multiscalar multiplication. FFT is another primitive that's often used, stands for fast Fourier transforms. And there's other little kind of parts. Witness generation is an important part of generating a snark end to end. So there's all these components, and for a variety of reasons, which included resources, but also, quite frankly, it was a result of how to create a judging that was fair in the short time that we had to structure the competition. We focused on these primitives as a result of lack of time and resources. But in the future, and when I presented about where I would like ZPrize to go this morning, obviously, first off, we want to make it a community-owned public good so that hopefully all of you in this room and beyond this room can decide what direction does this go. But for me personally, I think what is exciting is these end-to-end applications. And by the way, this extends beyond just hardware. I think everyone here, this is called the ZK Summit, for God's sake. So we all believe in the potential for zero-knowledge cryptography, but there are precious few real-world products that we can point to that use this technology, right? And I think I was having this conversation with someone earlier today that standards, oftentimes, it's very important. I believe strongly in stuff like ZPrize, obviously enough to kind of found that initiative, and I think standards bodies do play an important role, but oftentimes what can define a standard is not a group of people, but a market that demands something, right? And so that's why I think it's important that the ZPrize not just exist in a vacuum of, say, let's make MSMs faster for no reason. It exists in the context of, hey, how can these accelerations, how can these improvements enable use cases that enable products that enable a market? And then the market will give feedback to the companies, many of whom are sitting on the stage, and then that will drive innovation in a very natural way. And so I think, to me, the direction, if I had unlimited money and resources, it would be to try and get as many end-to-end use cases that we think today are very high potential for zero knowledge or other forms of advanced cryptography, and try and build a competition around that and build excitement around that competition and hopefully inspire companies that are not hardware related, but just saying, hey, if I had this tool, I would be able to build this product to inspire them to, to then build products that consumers would go on and use. I don't know if that's an answer, but that's kind of what I think.
Any other questions?
Yeah, thanks for great session. I have a question. In the past, there were a few hacking challenges with Xilinx FPGAs when people were giving away FPGAs like for free in exchange for some open source contributions. If you had a ZK-themed hacking challenge on Xilinx FPGAs, which way would you prefer to go? To use Amazon Cloud FPGAs or like maybe install some new FPGAs on Amazon, or to give away new FPGAs to people and see how it works? Because in some cases, first of all, it's embedded hardware. You have to press the power button a few times just to reprogram the FPGA. And another use case for physical FPGA is when people use replacements for Xilinx runtime. So I've produced such a replacement where you have an open source shell, which you can combine with your processing element in the end you can do some design iterations on the processing element to optimize it, and then you can fuse it and get higher clock speeds from the fuse design. Yeah.
Yeah, that's like several questions bundled into one. You mentioned the shell design and the shell design on 16 nanometer versus 7 nanometer. So I don't want to get a little bit too technical on that, but definitely kind of our approach. So for the last couple of years, our approach with a lot of these FPGA cards, so you buy FPGA as a silicon, that's kind of different, but we had these Aleo cards and Varium cards that you would buy. And our focus initially was in terms of supporting the community, we were really trying to focus on Vitis with the mindset that eventually Vitis is going to be the most optimized design. And it has improved, to Omer's point, quite a bit. But 50% is not 100%. So this year, we are trying to really kind of make Vivado a first-class citizen. And when we say Vivado for the rest of the people in the room, that's when you really treat FPGA as an ASIC. You really go at low-level hardware languages, right? So we are going to have Vivado shells available so that if you want to really if you're a hardcore FPGA developer and want to optimize everything and don't want to design your own shell, we are going to provide those resources, and then still you're going to have Vitis available to you. For people who still want to experiment, but really we are going to focus on people who really want to create optimized solutions on FPGAs. So that's kind of the approach moving forward. And then when we move to Versal, which supports PCIe Gen 5, the shell architecture is going to be quite different because we have a lot of hardened blocks. So in the 16 nanometer, you have to do your own DMA and your own PCIe block. But in Versal, all of that is hardened, so you can have a much more modular approach to how you design the shell, and shell is kind of like an operating system for the FPGA, basically. So there's going to be quite a lot of improvement as we move to Versal as well.
And I think with that, what I'm going to do here at the end, I want to give each of our panelists a chance to just quickly say what they're excited about, just in general, about the future, where they could speak about your company, speak about ZPrize, speak about zero knowledge in general. So this the last kind of few moments here, we'll pass off to the panelists to kind of share a little bit with you all what they're excited about for the future of hardware acceleration in ZK.
Yeah, I think this was kind of talked about before in some sense, but the infrastructure level in terms of ZK, at least last year for the ZPrize, like a lot of these primitives that people focused on, like MSM or NTT or witness generation or some of these other primitives, like they were very successful in helping like launch some of these applications, right? Like without those like primitives, like you can't really expect an industry to develop and markets to develop around that. And I think right now we're in this sort of phase where a lot of these applications are now leveraging a lot of these primitives so that they can actually scale to a degree where users can come in and there's sort of like you can support this like sort of large demand. Right now I'm super excited about some of the light client stuff that people are working on, supporting some of those primitives. How do we get like these applications in front of users? So like applications like ZK gaming, where you're actually leveraging privacy to, in some sense, to help actually use the game on chain. There are a bunch of these different applications, but I'm more excited now about like user facing and like UX improvements as a result of like using zero knowledge technology, as opposed to some of the more infrastructure and primitive work that people have been sort of focused on for the past year and a half.
So for us this year, so last year we experimented, accelerating NTTs, MSMs, kind of one-offs. This year, and to Alex's point, kind of with the end application in mind, we are very excited to figure out how we can have reference hardware platforms that accelerate the whole application. So kind of this concept of whole application acceleration when it comes to ZK for a specific end applications and really make the adoption of those end application at a scale possible. So that's what we are very excited about.
So one of the questions I've been asked a lot is, where do we focus more on Web3? Where is our focus on Web3 or outside of Web3? And my response is, where do you draw the line, right? Because ZK is a fundamental technology for removing trust from a system. I mean, at some point in the future, there is going to be, I assume, Web3 is expanding, right? It's basically we are decentralizing more and more functions to benefit of mankind, and also we add privacy and so on. So for me, I'm most excited about seeing this like border or this like expansion of Web3 using ZK technology.
Let's give our panelists a hand here.